guys, it's Mrs. Millison. Okay, today we're going to learn about binomial distributions, okay? And binomial distributions is just another extension of probability, okay? So let's start with, it's a known fact, or, chicken producers say that 70% of people like chicken, okay? So if I ask you what's the probability one person likes chicken, okay? So what's the probability one person likes chicken? You'd say 0.7, right? What's the probability two people like chicken? So then I think, okay, I think I'm going to do a tree. So the first person, they like chicken or they do not. Oops. They like chicken or they do not. So it'd be 0.7 or 0.3. And then the second person, they like chicken or they do not. They like chicken or do not. And the probabilities don't change. So the probability that two people like chicken would just be down, this branch, right? 0.7 squared. Okay. Probability 5 people like chicken, okay? I would have to continue my branch, but I know it would be that top branch of all 5 people liking chicken. So I would say 0.7 to the 5th power, okay? So we can do this because each person is independent of the other person, right? The probabilities aren't going to change. There's only one outcome when we ask a person if they like chicken. They're either going to like it or they're not, okay? And that's it, okay? So I can just keep doing a tree. But binomials come into play when I have a total of 5 people and I want to know the probability that, say, 2 out of the 5 like chicken. Okay, so what's the probability that 2 out of 5 people like chicken? Okay, now I could build a tree, all right? And I could build a tree for all 5 people, and I've done that. Okay, so here's my tree of 5 people, asking 5 people if they like chicken. So this is the first person. They either like it or they don't. The probabilities are the same. And then the second person, they either like it or they don't. They like it or they don't. It doesn't matter whether the first person did or not, independent. Okay, so the probabilities don't change. This is the string of the third person liking chicken or not, fourth person, and fifth person. So if I want to know what's the probability that 2 out of 5 people like chicken, I've got to find the branch that has 2 people liking chicken, okay, so that would be 0.7 squared, and then the other 3 people not liking chicken, because those are the 2 people that like chicken, 0.7 times 0.7, and these are the 3 people that don't like chicken, okay, so that will be my branch. So here's 2 people liking chicken and 3 people not, okay, here's 2 people liking chicken and 3 people not. Let's see down here. Here's 2 people liking chicken, 3 people not, okay? So you can see this 2 out of 3 people, or 2 out of 5 people liking chicken has multiple branches, okay? Every branch is gonna have that same probability calculation, okay? So this branch up here with 2 people liking chicken and 3 people not, it's still gonna be 0.7 squared and 0.3 to the 3rd power. This branch with 2 people liking chicken and 3 not is still going to be 0.7 squared and 0.3 to the 3rd power, okay? The question is, how many branches, okay? So I would have to figure out how many branches, do this multiplication, and then add them all up, okay? Or I can just multiply right here by the number of branches, okay? Now, I could figure that out on my little tree here, okay? I could figure out how many branches. But we want to figure out a faster way to do this, because what if I ask you, out of 100 people, what's the probability that 20 out of 100 like chicken, okay? You're not going to build a tree for 100 people and sit there and count all the branches that have 20 people liking chicken and 80 people not, okay? That's just too much. So what we're going to use is a binomial distribution, okay? There is a formula for it, and you have to be familiar with the formula. But this is the formula, okay? The formula is the probability of success, so success in here is that the person likes chicken, raised to whatever power of the number of people you want to know that like chicken. And then the probability of failure, so not liking chicken, and then the rest of the people, because this is out of 5. And what we would do here is we would have a combination, okay? We would say 5, choose 2, okay? Now, you don't need to worry about that, how to calculate that combination, because that combination will get us our number of branches. This is what the formula looks like, pre-calculator days, okay? But in our calculator, we can use something called binomial, spelled binomial wrong, PDF, okay? So what binomial PDF is, it does this entire calculation for us. It basically builds itself a little tree in there, figures out how many branches have this, this series of multiplication along the branch, okay? And then it gives us our probability, okay? So binomial PDF is found under second vars, same place we find normal CDF, but we're gonna scroll down. Okay, there's my binomials. We'll do PDF and then we'll do CDF. PDF is for a single value, 2 out of 5. CDF is for a cumulative value, and we'll do that in a second. So I'm gonna go binomial PDF, and then it's gonna ask me for the number of trials. The number of trials is the total number of people. So I'm gonna put 5. P is the probability of success, probability that they like chicken. So 0.7, because that would be a success in our situation. And then X is the value we're looking for, 2 out of 5. Okay, so I put that in there. Now, if you're gonna use this on the AP test, they don't like calculator ease, so you've gotta label this. This is the number of people. That's the probability that they like chicken. And that's just my X. You don't have to worry about that. Okay, so there's a 0.1323 probability that 2 out of 5 people like chicken. So this is the same number I would have gotten if I had found every single branch that had exactly 2 people liking chicken and 3 people not liking chicken, okay? And I'll give you a copy of this, so if you want to work through it and you can see it, okay? Okay, so knowing this, I can actually create a probability distribution, okay? So I'm going to say number of people that like chicken, okay? And then the probability, okay? So out of 5 people, of course this is out of 5, I can have nobody liking chicken, 1 person, 2, 3, 4, or 5, okay? The no people and the 5 people, that's just, those are the top and bottom branches. This is 5 people liking chicken, right? 0.7 to the 5th power. And 5 people not liking chicken is the bottom branch, 0.3 to the 5th power, okay? So this would be, I'm gonna put down here, 0.3 to the 5th power, and this would be 0.7 to the 5th power, okay? But I'm gonna do it in the binomial as well. These are the ones that have multiple branches, okay? So these are the ones that I don't necessarily wanna go through and sit there and count all the branches. I could in this situation, because it's only 5 people and the tree is very manageable, but what if I said out of 500 people? You're not gonna sit there and build a tree for 500 people, okay? So we know the probability that 2 out of 5 people, so I know that this is 1, 3, 2, 3. So let's find the other ones. Now we know, I'm gonna do these 2 first. We know that 0.3 to the 5th power, okay, is 0.0024. Let's do it as a binomial. So now binomial PDF, still 5 trials, still probability of success is 0.7, but now my X value is 0. So this is what's the probability that 0 out of 5 people like chicken. And it should be the exact same thing, okay? Okay, now I'm gonna come up and take this and I'm just gonna change this to 1, okay? So this is gonna be the probability that 1 out of 5 people like chicken. So this is I didn't put my zeros in there. 0.00243. I'm not gonna have enough room here, am I? 1 is 0.028. 2 is 0.1323. Let's do 3. 0.3087, and then 4. 4 out of 5 people liking chicken. 0.3602. I'm just gonna abbreviate a little bit, or around, and then 5. Now 5 should be the same thing as 0.7 to the 5th power, because, I didn't put 4. I didn't change the 4 to 5. So 0.7 to the 5th power and putting a 5 in there, 5 out of 5 people liking chicken, is the exact same thing. Okay, now if I add up all these probabilities, what are they gonna equal? They're gonna equal 1, okay? If they end up equaling 1.0000 something, that's okay, or 0.999, that's okay too, it's just rounding, okay? So I can build this probability distribution, okay? And from this, now I can ask you even more questions. Not only can I ask you, what's the probability that 3 out of 5 people like chicken? Now I can ask you something like, what's the probability that at most, okay? So the probability at most 3 out of 5 people like chicken. So what does at most mean? Okay, that means either 0, 1, 2, or 3 people could like chicken. Okay, so if I have a table like this, that would be easy. I would just add all that up, right? Okay, so if I do this from the table, let's add it up. 0.00243. Oh, I don't want that one. That's 4. So this is the probability that at most 3 out of 5 people like chicken. So it could be 3 people liking chicken, 2 people liking chicken, 1 person liking chicken, or none, because that's at most 3. Okay, so I would get 0.47143. Okay, not too bad when I have a table. But I need to figure out another way, because what if I say out of 500? I'm not going to have this table. So we can use a play on the binomial PDF, but it's going to be binomial CDF, because it's going to be CDF, because it's going to be cumulative, okay? And just like when you come in here, when you come in here and choose normal CDF, remember when you choose normal CDF to do a normal distribution, to find the proportion under the curve, it's always to the left of the curve? Well, binomial CDF is also to the left of the number that you put in, okay? So when I choose binomial CDF, I still have 5 trials. I still have the probability of success being 0.7, but what I'm going to put here, and I call it my anchor, is the value of x that it's going to accumulate the probabilities from and then go to the left, okay? So if I want 0, 1, 2, and 3, I'm going to put 3 in here, okay? Because that will accumulate the probabilities for 3, 2, 1, and 0, okay? And this should be pretty much the exact same thing. My rounding might be a little off. Yeah. So 0.47178. Again, my rounding's a little off because of that rounding, okay? So this is a lot faster, okay? Now, what if I want to do, let me get another one here. What if I want to do the probability that at least 2 out of 5 people like chicken? Oops. Okay, and again, what's at least 2 out of 5 mean? So it's at least 2, so it can be 2, 3, 4, or 5. So if I have a table, I can simply add these up. Okay, so that's the probability that I'm going to have at least 2 out of the 5 people that like chicken. Okay, but let's use our binomial CDF. Now remember, binomial CDF goes from the x value to the left. So what I really want is at least 2 out of 5. I want all these, okay? So I would kind of draw a little line here. 1, 2, 3, 4, 5 to represent my possible outcomes. And I say at least 2 out of 5. So I want all that. So if I'm going to the right, what I'm gonna do is I'm gonna use my 1 minus. Because remember, all these probabilities add up to be 1. So if I add up all these probabilities and then subtract these 2, I'll have the 2 out of 5, okay? So how I write that in my binomial CDF is I do 1 minus binomial CDF, that's a D, still total of 5, still probability of liking chicken, but this number has to be the anchor that it's going to accumulate to the left. So I'm going to do 1. So this will accumulate these 2 probabilities. It'll add them up and subtract from 1, which will leave me the difference, which is what I want, 2, 3, 4, and 5. Okay, so if we do this, so still 5.7, this time I'm going to change it to 1. Okay, and you'll notice it's the same thing. Again, rounding's a little off because I rounded. Okay, so using the binomial PDF and CDF is going to be a lot more efficient than having to draw a table every time. Because what if I ask you, Okay, so let's look at this from the standpoint of a different size of people, because I can always draw a tree for 5 people, okay? But let's say I have 150 people. I am not going to draw a tree for 150 people. That tree would be impossible to draw. But I want to know the probability that 120 of the 150 people like chicken. Okay, so I can still use my equation. I can say 150 choose 120. Okay, and again, it's a combination. Just understand that how to write it. Total out of the number you want. So the 120 people are going to be the ones that like chicken, right? So I'm going to have 120.7s, and then I'm going to have, what, 30.3s, because these are the 30 people that don't like chicken, okay? So again, I'm not going to worry about calculating. I just want you to be aware of that equation, but I'm going to use my Binomial Pdf. So it's going to ask me for Binomial Pdf, number of trials, which is 150 total people. Probability of liking chicken is still the same. And the x value now is 120. So I want to know 120, probability that 120 people out of 150 like chicken if the probability of liking chicken is 0.7. Okay, so that's a 0.0017 probability. Okay, like almost 0.2%. Okay, probably not going to happen. All right. Well, what's the probability? What if I want to know the probability? Hold on. But this was a lot faster than having to draw through a tree, okay? Because I'm not going to draw a tree for 150 people. 150 sets of branches, that would just take forever, okay? So this is key. But you also have to be able to recognize that formula, okay? All right, now out of our 150, what's the probability at most 115 people like chicken? Okay, so again, I'm going to use, so at most 115, so if I go from 0 to 150, here's 115, so at most is 115, so that would be 115, 114, 113, 112, all the way down to 0. So I'm going to use my Binomial CDF to accumulate all the probabilities from 0, 1, 2, 3, up to 115, because I'm not going to calculate those individual probabilities with a PDF. I know the one for 120 over here, but that's not going to be in this group, okay? And that would take forever, do 115, 116 really, individual probabilities. So I'm going to use my Binomial CDF that's going to accumulate from the probability of 115 out of 50 all the way down to 0 out of 50 and everybody in between. So again, it's going to ask me for the total number of trials, probability of success, and then it's going to ask me for that anchor number that it's going to start accumulating from on the left. Okay, so I want to include 115 because I want 115 down. Okay, so this will be 0.972. So there's about a 97% chance that at most 115 people will like chicken, because it can be anywhere from 0 to 115 people. Okay, all right, let's do an at least. What's the probability that at least 100 people like chicken? Okay, and again, I don't have a tree to look at, and I certainly don't have a probability model to look at, so I've got to use my binomials. So if I think from 0 to 150, I want at least 100, okay? So that's going to be 100, 101, 102, 103, okay? And I'm not going to calculate using my PDF for 100, 101, 102, 103, all the way up to 150 and add them up. I'm going to use my CDF, okay? But remember, cumulative totals from the left. So I'm going to take 1, which is the total of all those probabilities, and I'm going to subtract the pink part. Well, the pink part's going to start at 99, right? So now I'm going to do 1 minus binomial CDF. Again, 150, 0.7 like chicken, and now I'm going to accumulate from 99 to the left, okay? So 1 minus binomial CDF, still got 150, still got 0.7, so now I'm going to put 99 in here, okay? and there's a 0.8366 chance, okay, about an 84% chance that at least 100 people are gonna like chicken, okay, highly likely, just like this one, highly likely, at most 115, okay. So knowing how to use your PDF and CDF, and then 1 minus CDF for anything accumulated to the right, is gonna save you tons of time, because you will not have time to write a tree for 150 people. I mean, this is 5 people and it just fit on a whole page. I can't imagine how many pages it would take to do a tree for 100 people or 150 people. Anyway, okay. I think that's all I wanted to say. I will have some practice for you to do, and we'll go from there. Okay, thanks. See you later. Hope this was helpful.